I'll try my best to follow that last presentation. So I'm going to be talking to you about a trial in maintenance at London Underground. And the idea of this trial was to capture data from lift controllers and investigate its value for maintenance and asset management. So the reason why this was originally needed is because despite the fact most of our controllers on lifts and escalators are capable of monitoring a lot of information, we're not using it to its full potential within the business. So the idea was to demonstrate that it's actually a good thing to do. I worked on this with Virgil Yotoff, who is a system engineer and data analyst from Amy Strategic Consulting, and he did most of the development work of the system. So first of all, I'll talk about the background, which lifts we chose for the trial, and how the technology has enabled us to do the trial. The trial itself is in two stages. The first one was to put some local data logging technology on one of the lifts, capture some data, and then do some analysis to see what we were getting. The second stage was to make it remote, so actually make it a real-time system. I'll then talk about future developments and some conclusions at the end. So the lifts that were trialled were Covent Garden lifts, Covent Garden Tube Station. There's 4 lifts there. They carry over 47,000 passengers per day, so they're very heavily used lifts. They run 20 hours per day, and they were installed, they actually run 24 hours a day, weekends now for Night Tube. So although they were installed in the 1980s, they've been recently refurbished, and part of this refurbishment has included a control system that allows us to capture data. The maintenance is done by an external contractor. It's managed in-house. However, the maintenance, servicing, failure response, that type of thing is all done by a third party. So we involved them throughout the trial as well. So the controllers that we have on these lifts are programmable logic controllers, which many of you, I'm sure, are familiar with. The data that we can potentially get from these is quite extensive. So there's a lot of discrete signals available from faults that occur on the lift to limit switches and things like that. You can also see what control mode the lift is in, which is quite handy. And then there is some analog data as well. On 2 of the registers, you're able to get a range of values for the lift speed and lift position. So as part of the refurbishment, which happened about 4 years ago, this module was fitted to all 4 of the lifts, and this is effectively an interface module, which allows you to poll the data on that's on the PLC. It effectively replicates the data on the PLC, and it provides an interface which you can effectively just get that data read only. So there's no risk that you're going to take over control of the lift, or if there was a problem with the system, the worst thing that's going to happen is you'll get the data failure on here. Modbus was selected because this is a protocol we are using for some of our existing monitoring systems. So the idea was it would be compatible if the need arises to combine them together. So for stage 1 of the trial, I effectively just fitted a data logger, a USB data logger compatible with Modbus on one of the lifts, and this polled the Modbus module once per second and got the value of every register for each time it sampled it, and stored that information on a CSV file on the USB stick. So this resulted in lots of files. Each one was an hour's worth of data, and I have just given you an idea of what that information looks like. Most of the signals don't happen that frequently. On the right-hand side, the last 2 registers there are the speed and position. So you can see is a hexadecimal value. It starts to go up as the lift's accelerating. So this isn't particularly useful. So with some processing and some development work, it resulted in a list of events which make a bit more sense to the average person. And I've highlighted a safe edge fault which occurred during the period of sample data. And what we've been able to do is to overlay the times of that occurrence with the analog data. So it just gives you a historical picture of what's happened with that lift. And that was enough for me and for most people to say, this is quite a good idea, we should probably pursue this further. So the findings from stage 1 we recorded the details of the asset, as we expected. We found out it is useful. Everyone agreed that. And we found a way that we could visualize it to get some insights as to what's happening with the lift. There were some limitations with this system. First of all, it's not very scalable to put a data log on every single lift. It's a very manual process. You've got to go and collect the USB drives to swap them over. And the data is only available up to the last time that you went to get it, so you can't get, obviously, real-time data. The sample rate isn't brilliant. Once per second is slow enough that you might actually miss some events happening. If something goes on and off within a second or less, you may not even see that happening. So this led on to stage 2. And what this did is it's expanded the trial to all 4 of the lifts at the station. There's a central industrial computer. It's a Linux-based microprocessor, and that was on lift 2. And that interfaced directly with the Modbus module in the same way that the previous data logger did. But then what we've added to it is a serial to Wi-Fi, or effectively the Modbus to Wi-Fi adapters on the other 3 lifts. So it's completely wireless, which kept the costs down. It enabled us to do the trial very cheaply. So the idea was there's a local Wi-Fi network. The central master unit polls the other 3 lifts and gets its own data. And then it sends it to the cloud over 3G. So again, wireless. And Mqtt is the system developed by Amy Strategic Consulting. So this is a cloud-based asset management system with the capability of processing data, visualizing it. And Virgil was in the process of developing this system at the same time. So he was developing it along with the data that was coming out. So it was sort of growing as this did, really. You'll see there Mqtt. Is that there? It's a little... I'm not sure where the light... Not that one. Oh, that's it. Okay. You've probably all seen it by now anyway. Mqtt, so this is the protocol which was used to send the data that had been collected and processed from all of the lifts. The reason for using this is it's a very lightweight protocol. It's very good for low bandwidth, and also it's quite good if you've got any connectivity issues as well. So it's very suitable for Internet of Things applications. So just a bit more about the hardware. This was the unit that was installed on lift 2. Some of the spec there, so you can see it's quite flexible. It's got the built-in modem, and it also has flash memory installed as well. And if you're interested in how it actually works, it's got a Raspberry Pi compute module inside it. So it's all built on that with extendable sort of expansion to it. On the other 3 lifts, this is the adapter. So it was this was a very low-cost adapter connected to the Wi-Fi the Wi-Fi network that was created locally, and it was contained within the machine chamber, machine room. So I mentioned Mqtt. That was allowed us to send data effectively, but most of the processing was actually done on the cloud. So the visualization and further analytics that could then be done, that's all done on the Mqtt system. And there were a few security features. First of all, I mentioned that the Modbus interface is read-only, so it prevents any unexpected or unwanted control of the lift itself. We also used transport layer security and a virtual private network to encrypt the data that was sent over 3G, and also had a firewall configuration. So in the event that anyone is interested in the data, they wouldn't be able to make any sense of it. So I mentioned before you could add signals to the PLC and to this module. It had a few spare registers on it. So speaking to the maintenance contractors, we were able to add some more signals to it. Mostly entirely around the doors, which cause us the most problems because they're the main interface with the 47,000 passengers getting on and off the lifts. So we wanted to have a better view of what was happening with the doors. So we managed to get some calculated values. So these were timings for the doors, and then also some more discrete values based on the the door opening and closing signals in safe edge, which have turned out to be very useful. So this is what, once the stage 2 of the trial had been set up and we had all of the data coming out, this was how Mercury was developed to visualize it. And it looks like a lot of information on there, but the basic idea is there's a row per signal, and it will tell you when the signal comes on, which is the start of the bar, and when the signal goes off, which is the end of the bar. So you can see there's quite a repeatable pattern when the lift is behaving normally. And what you can see over to the right-hand side is a vertical red line, which indicates a fault being raised by the station staff. So in this case, it was the door was out of adjustment. But the interesting thing is, earlier on in the day, so this was about nearly 3 p.m., about 2:30 p.m. there was an event, and there was also one just before midday, both related to the doors, and both reset locally by the station. So the maintainers wouldn't have been aware of these events occurring. They may not be related, but it shows that there may be some early warnings for faults that this system can potentially pick up. So another benefit we found from it was where faults were being picked up quite a long time after they'd actually happened, we were able to see it on the system. So in this case, you've got an AC drive system fault. This is one which needs to be reset by the maintainer, so they need to be called out. The lift went into fault just before 1 a.m., which is when the lift was shut down for the night. No one realised until the following morning when the station staff tried to start the lift up and they realised it wasn't working. So that was the red line, again, is the point where the fault was raised, maintainers went out and they rectified it. If this system was set up, and it's possible to do so, to alert the maintainers of particular faults that you know are serious, that would have been an email or even a work order raised to the maintainers, saving quite a lot of time potentially. Luckily they did get to site quite quickly, but if it was just before rush hour and the lift wasn't working, you can imagine the effect would be a lot more serious there. And another interesting finding was that on a couple of occasions there were faults raised, and just before the fault occurred, the control mode was switched between auto and landing control. And we thought this might just be a bit of a glitch in the data or something like that, but did some further investigation and found that the station staff actually were doing that deliberately to speed up the flow of traffic through the station, which isn't ideal, but it obviously was allowing the lifts to move before they would have otherwise done so. But the problem was, if that was done at a certain point where the lift was approaching the top landing, or lower landing, I think, the PLC didn't have time to adjust and it went into a fault condition. So we were able to then feed that back to the station, and now, since then, have been looking at actually programming the controller to not do that, basically. So the findings from stage 2, we've got remote access to the data. We've enabled real-time analytics, so as soon as the data is captured, within a very short time, it's available on the screen, and to whatever other system we needed to send it to. We can react to more faults more quickly, or more accurately, the maintainers can react more quickly. And the data rate improved as well, so by 10 times. So the polling interval is now 10 times per second, which is the maximum that's available with the Modbus interface module when the PLC updates that. So we've basically gone to its full spec there. Again, there are some limitations, and these were around the connectivity of the system. So the Wi-Fi to Modbus devices weren't particularly reliable, specifically the ones that were further from the main lift. And we think that was possibly just the strength of the signal. We deliberately didn't want one that was too strong, but it turns out we've probably gone the other way there. Potentially, it might be worth just hardwiring them for the sake of knowing that it's reliable, but at least we have proved the concept. And then the 3G connection was also a bit of an issue as well. That did seem to drop out, but we managed to get around that using the Mqtt local storage, and also to save on the amount of data that we were using, because obviously there's a SIM card, you have to pay for that. We managed to reduce the amount of data by only sending what's changed. So rather than saying this is still the same, this is still the same, this is still the same, we managed to reduce it by doing that. So this is where it can potentially get very interesting, and I think a lot more data would be required to do to do this justice. But some initial investigation into the events, or the sequence of events, found that there is quite a stable cycle, which you could kind of see from the other plots there, that it's quite a similar pattern all the way through. But this shows you the order of the events each time the lift goes through its cycle. Most of the signals happen in the same order. There's a few variations in there, but this gives you the basis of starting to apply machine learning and identify anomalies automatically. There does need to be that amount of data, which I think maybe we do need quite a lot more to do it effectively. But with that and the maintenance records, feeding in and training the algorithms, that can get better over time, more accurate. So other further uses for the information. This is just a little screen, or big screenshot from the Plan Your Journey feature on the TfL website, Transport for London website. What you can now do on there is you can say, I only want step-free access, and it will tell you which routes you can take that avoid using escalators or stairs. This is great if your information is up to date. If a lift's just gone out of service and the website still says follow this journey, this route, someone will arrive there with a pushchair or in a wheelchair and find, oh, the lift's out of service. So by having this real-time data, this is another application for that data where you can actually either update the website via an API or some method, or update someone within London Underground who can then sense check it, say yes, that machine's out of service, then they update the website. But it's definitely a lot more of an improvement than we're at the moment. So in conclusion, we found that the controller data, it has improved, or it can improve fault response if alerts are configured correctly. And that's obviously an area for further work. It can be used for diagnostics, and that can be done remotely as well. So if a fault does come in, the maintainer can prepare as they need to, take the right spares and things like that, based on the knowledge about what they think or what the lift is saying is the problem. And asset management as well. So you just get a more of a detailed view over time of how your lift is operating. So for long-term strategy and for operations, to see where passengers are travelling and that type of thing. There's lots of uses for it in that area as well. So there's actually a lot of information that we already have effectively, because all we've done is we've just taken the information that's there. So the recommendation that I'm making is that we actually tap into that. It's not always easy. We've managed to do this with the PLC with support from, with collaboration from the supplier who supplied and maintains that PLC. Not all of our controllers have that particular design. Some of them are commercial companies, and access to data and access to the controller to get that data is very, very difficult for understandable commercial reasons. So we've had to be a bit clever in some cases about how we get that data out using other methods. But ideally what we should be doing is at the stage of projects, buying the lifts or refurbishing the lifts, put that in the scope, and then it's all set up at the time, rather than trying to retrofit it, which isn't ideal. And this solution can be adapted to other controller types. It's effectively a little computer. It's got serial input. It can be programmed to accept different signals. I mentioned we had to be a bit clever. One of the other projects I did with Virgil was on a microprocessor controller, and we couldn't get really any information via the serial port. So we had a camera set up, looking at the lights on the board, and then sending that to an image processing algorithm to look at which lights were on and which lights were off, which was actually surprisingly effective, as long as it didn't get dusty or get knocked. But we figured out ways around that. So the technology is, I think we've sort of proven that does work, but this is only part of the puzzle. You need people in place who buy into the idea. The process is to allow them to actually use the system. There's change management involved if you are getting people to use new systems, and this is only one part of a strategy. You're probably going to want to be monitoring other parameters from sensors and things like that if you really want to get the full picture. So there's lots of things to consider, and there's more detail in the paper, which hopefully might answer a few extra questions, but I'll be glad to answer any questions you have now. Thank you very much.